And I'll ask you to get whoever pops in. Two people entered the waiting. I'll ask you to cover the waiting room for me, Jeremy.
All right.
Welcome everybody. I am. We have a full agenda, so I'm not going to do a dog and pony show. I do want to mention one thing, and that is I get a lot of emails because they love to just send email to president at dvaa.org. And as just besides the one from the Nigerian princes, I got one from the Delaware Astronomical Society, which has a book club. And on Thursday, January 28th at 7 p.m., they're going to be talking about Beyond Weird by Philip Ball. And I foolishly thought, oh, that sounds interesting. So I signed up for that cruise, and I've now been wading through Philip Ball's book. I'm about 2/3 of the way through now. He's an amazing science writer, writes about a number of interesting things, but Beyond Weird is about quantum physics. And which is, I mean, I never even took physics, let alone quantum physics. But it's extremely accessible. It's very interesting. It's the because he's in England, he can't join the conversation, but it looks like Dr. Matt Brabowski will be overviewing the book and hosting the discussion. So if anybody's interested, email me at president@dva.org, and I'll be happy to send you the information, and you can sign up for that too. And with that, I'm just going to kick it off to our subcommittees and so forth, and it goes to you first, Brian. Who's muted with his video off. There you are.
All right. Sorry. We have 2, 4, 6, 8, 10, 11 new members this month.
Wow.
And a couple of them are here tonight. Katie and Scott are here that I did see. So it's Katie, Daisy, Martin Jones, Shashira Verman and his family, Monica, Tara, and Annika, Corinne Jacob, rejoining an old member, Dave McDougall, Mike Cogbill, and Michael Kemple. So welcome.
Thanks. And Brian, make sure you send me the information for the ones you didn't send me yet, because I am going to contact every single one of them.
Okay, I think just Scott, but I'll double check.
Okay, thank you. That's great that we still continue to grow members. That's really incredible. So now, Lewis Berman, it comes to you.
Yeah, so along that line, I think I said yes earlier on the meeting. We have 138 people who are current, and we have 41 who are not current right now, but 3 or 4 of them are, I'm sure, going to be current pretty soon. This is actually pretty damn good at this time of year. I mean, historically, we've seen, but in February, I'll be reaching out to all these people again, and we'll see what to do. You know, I know it is. You might say, why does it matter? And you know, your dollars help us do our mission. So thank you very much. If you haven't signed up for this year, it's super easy. Go to the website, log in. There is a button that in the upper right hand corner that says, you know, it's a red $sign. Click on it, follow the instructions, easy to do. And if you don't know how to do it, go to the website, click on the support link, and you can get a phone support person to help you out. Thank you very much.
Thank you, Lewis. So Andrew and Lou, you guys want to flip a coin to see who goes first?
Go ahead, Andrew.
Yeah, so I can go. I got wind that Lou wants to share something tonight, so I just have a really quick something to share. So good to see a few new faces. My name is Andrew Hitchner. I'm the observing chair for the DVAA, and this is my observing report for January 2021. And before I get into the main topic, I did want to congratulate Jan for reaching the Stellar Level Outreach Award. So congratulations, Jan. Jan recorded at least 52 hours of outreach program, which, to be honest, I feel like is a little low. That's what just what she recorded, maybe. But congrats to Jan. And I do want to point out to everyone that this is a very obtainable award. To get the base level, you only need, I think, 5 or 10 hours. So if you do 1 year of star parties, you're going to get there. So keep track of your outreach. And it's great to get this award and see people getting out there and doing something great with the community.
Thanks, Andrew. And if I could just add to that, we've tracked all of the outreach events on a spreadsheet since 2017. So if you'd like to apply for this award and you just don't remember which events you did, you can check the spreadsheet document will remind you. I have the names and everything in there of who participated. So the way you find that, it's under the club documents under outreach, and there's a spreadsheet for every year. So that's where I tracked my stuff. Worked really well.
Awesome. Thanks, Jan. Yeah, that's awesome. Even easier. So if you're interested, go look at the Astronomical League's website. You can find out more about the award there. So like I said, I have something just really quick. Being a new year, seeing that we've picked up a few new members and we haven't really had that face-to-face time, especially on the observing field that we usually get. I just wanted to go through and run down all of the DVAA dark sky observing sites we have. We only have a few. I'm going to go through. I do want to point out that all of this info I got from www.dvaa.org under observing and then observing sites. You can find directions there. You can find who to contact about going there, any permits that are required to get there. So if you want more information, go look on the website. It's a great resource. So we have 3 main sites. I'm going to go through each one. I do want to point out Valley Forge is not an observing site that we can use. We have special permission to be there for the star parties only on those nights and only until 11 p.m. So please do not go there unless it is a designated star party event. So first I want to talk about French Creek State Game Lands, number 43. You can see here on the map, so King of Prussia and Wayne around here. It's probably about an hour drive or so. I live in Phoenixville, so it's pretty close to me. It's technically a Bortle 5, which I think it might be a little higher than that. Higher being more light pollution. It's degraded pretty much since I've gone there. I haven't been there in a long time. Maybe it's improved a bit. But I would say that it's maybe more of a Bortle 6 now. But it is a very large open area. It's on the gun range. There's plenty of spaces for cars and equipment. You can only go on, though, after the shooters are done. I know that they're supposed to be done by sundown. They usually aren't, but it's just better to wait for them. The gravel road also can be a little bit treacherous. There's several big potholes last time I was there, so make sure you take it pretty slow. As far as horizons, it is pretty good horizons to the north and south. The south probably being the west, or being the best horizon. Unfortunately, the western horizon is pretty blocked by trees, unless you go pretty far out to the field. The road is along the west, so we tend to park closer to the trees on that side. So if you're planning, you want to see things on that side, just make sure of that. Now, this one, you do need a permit. I have never been asked to present a permit while I've been there. I have heard stories of people being asked. We have one on the website for members only. It's under Documents, Observing, and Permits. That permit is good until the end of 2022. So if you are planning on going out there, make sure you have a copy of that in your car. Next one I want to talk about is probably one of the newer ones that I've started going to is Green Lane State Park and the Knights Road. I think this is the Red Trail parking for that. This is a Bortle 5 as well on the night sky map. I do think it's a little better though than French Creek. There's pretty significant sky glow, especially around the horizons, maybe in like the northeast area towards Allentown, but straight up, it's actually really good. You can easily see the Milky Way from there. It has good horizons as far as obstructions go, and I mentioned the sky glow. Oh, and of course the southeast as you go towards Collegeville and King of Prussia there. This is the designated observing field for Green Lane State Park. So you are allowed to go without a permit. Now, usually the local policemen are patrolling up Knight Road, and we have had them stop just to kind of check out what we're doing. You know, although they've been more aware of us coming now, so it actually hasn't happened when I've been there, but I've heard stories of other people where they stopped by. But they're usually really friendly, I've heard, and pretty interested in what we're doing, and it doesn't really cause any issue. So just be noted of that. And of course, it's only a short trip from Candlewick Observatory, which we'll have a live stream from later. So be sure if you're going out there, maybe hit up Lou, and there's always a lot of hospitality out that way. But this is probably the one that I've been most frequently going to, about the same distance from Radnor and King of Prussia as French Creek. Now, our darkest site would be Blue Mountain Vista Observatory. This is private property is owned by Frank Colosimo. So make sure you notify him when you're going out there. But he's usually always welcoming to let people go and use the field. You can't actually see the house. The field is shielded by trees from the house, so that's good. It's technically a border of 4.5, and it's pretty good for just an hour and a half to 2 hour drive away from the city. So if you want to go somewhere slightly darker than like not Cherry Springs, Green Lane State Park or French Creek, definitely go here. I have found that the field can get a little crowded. Really just with the car situation, it can be a little difficult to navigate with cars. So if you're going to stay overnight, which we frequently do, make sure you park near the end of the field away from the road, and let people who are leaving sooner in the night park closer to the road. Generally a good idea in any observing site. And you can find out more about Blue Mountain Vista Observatory at this website down here. And if you go to the DVAA's website, there's links also there. And of course, if you do use this site a lot, please drop Frank a thank you, either a note or monetary donations. He does a great job with that place, and it's really out of the kindness of his heart is the only reason why we get to use this location. So thank you, Frank, for that. So those are the three main sites that we use. But if you go somewhere else, please let us know. It's always great to find out other places to go. There are a few ways that you can do this. You can go to the Observing Forum on the DVAA website and talk about things there. You can link that to your email so that whenever there's a new post or a new discussion or comments or anything, then you get sent to your email, which is great. And of course, we have the groups.io email as well. It's also a good idea if you're going out, just let people know when you're going out, no matter what day, no matter how long you're staying for, who knows who might show up there. So, and if you have anywhere else, let us know. We're always welcome to hear where you go, because it's a little tricky finding observing sites. You never know where you're allowed to go, how good it is or anything. So yeah, that's what we're here for. That's what the club's for. And again, short one. That's all I got for you. I'll relinquish control.
Thanks, Andrew. Appreciate that. Harry, where on Long Beach Island?
So, do you know? We actually stayed in a hotel called. Trying to think of the place. It's on Ship Bottom.
Really?
Yeah, and so we were right on the beach, and there was not a whole lot of light pollution there, but you could set your gear up on the beach, and you could actually see the Milky Way.
Wow.
It was amazing.
That's awesome. I love Long Beach Island.
I prefer the northern end. We were in Barnegat Light in September, but it was pretty much cloud. I took my stuff down there, but it was cloudy pretty much every night, or at least not good observing.
There's a guy, his website's, I think it's milkywaymike.com.
Uh-huh.
He has a list of all the locations on the Jersey Shore where you can get good Milky Way panoramas. And I think his number one is, I'm trying to think where, but I can look it up. I can post the link on the chat.
Thank you.
Yeah.
Thank you. Um, okay. Now there's something special happening, and our chair of astrophotography, Lou, wanted to bring it to our attention. So, Lou, take it away.
Okay. There's going to be another ISS transit of the moon soon. In fact, it's going to be tomorrow. And it's going to happen where a lot of members live. So if you guys would indulge me, let me talk about it and explain to you how to take a picture of it if you'd like. Now, I want to preface this. I've never actually taken a picture of the ISS transiting the moon, but the technique that I'm going to tell you is the same type of technique that I use when I image the moon, and it should work. The most important part is timing, and we'll talk about that. So give me a second here to share my screen. Right, let's see here. Okay. So let's go over quickly some details. You have to be prepared to do this because the ISS zips around real fast, especially when it's against the moon, because it's, that's only a half a degree across the sky. So, all of you are familiar with this general information. You know that you can see it with the naked eye. You don't need a telescope. When it passes over the Earth's shadow around, twilight. So the ISS is above the Earth's shadow. It still sees the sun. We're in the darkness. It reflects down and we see it. It can get really bright. Sometimes even brighter than Venus. All right. So it's very important to know exactly when the transit's going to happen. And the key to this is getting your time synced accurately. The ISS, all those times are off of the atomic clock. Now you can go to a server on your phone and download the time within hundredths of a second. They'll guarantee accuracy, but then you still have to deal with the latency of the network that you're on. So I know that if I'm on my desktop and I check the latency, it's 0.3 seconds maybe, but my cell phone might be 2 seconds. That may not seem like a lot, but when it takes 0.7 seconds or 0.5 seconds for the ISS to transit, you already missed it. So it's important to get that straightened out and be aware of that. So there's a phone apps you can do. There's one called ISS Transit Prediction that you can get on an Android. Or if you use your desktop, you can just go to transitfinder.com. And let me see if I can click on this. And if you do, here we go. We'll get some past information here. It shows you how big the ISS will be across the sun or the moon, how far away it will be, where with respect to the moon or the sun it's going to transit. Now, this obviously depends on your location. And it gives you a bunch of other information here. This particular one says it's going to be illuminated, but that's a little bit misleading, and I'll talk about that in a sec. Another thing you want to look at here is when you're finding a transit that you want to photograph, you want to try to select one that has more than a couple of stars. Because then it just shows here when there's only 2 stars. Look at the size; it's really, really small, 21.2 arc seconds. That's why they give it only 2 stars. This one's going to be a little bit bigger, so it's 3 stars. Now this one is going to be even bigger. It shows you here the angular distance, 60 arc seconds there, but it shows you at the location from where this is at. It's way off center. So if we look at it on the map, we can see exactly where it is. I think, let's see here. Okay, so if you're in like the Target shopping center parking lot at 4:30 with your camera, there you go. Now, this may sound like it's simple, but it's not. The hard part is during the daytime, especially if you're somewhere like the parking lot of Target, which you can be when you're doing, when you're imaging the moon or the sun, you don't care about light pollution. The problem is polar aligning. And the reason why that's an issue is, you have to be zoomed in pretty tightly to see the ISS because it's very small. If you're zoomed in enough and the moon moves out of the field, obviously you're going to miss it. So polar alignment comes in very handy. It's not, you can still do it without aligning, but it's not 100% necessary, just easier. If you have a mountain, you want to do a solar align. And I would only recommend you do that, obviously, if you have a solar filter. Or if your mount allows a lunar align, you can. But if you have a tripod, then you just have to do it manually. Okay, so depending on where you are, these numbers will change. The time that it transits is always being updated. What I would do is get there around the time, make sure you focus everything, set everything up, pointing in the general direction of the moon. And half an hour before the transit is predicted to pass, I would update the orbital elements to make sure that you're synced. The one way to collect the data for this is to use burst mode on your camera. So you can set your camera to your telescope if you've done that before. If not, you can use a long focal length lens. With some cameras, you can get pretty good zoom without the use of a telescope, and I'll show you that in a second. But that method does not work with all cameras. Typically, you won't be able to do that with a Nikon camera unless your Nikon is attached to your telescope. You're not going to be able to use the digital zoom feature on that. So test your camera on burst mode. Do this before you go out. See how long it'll burst for. A lot of cameras may only burst for 3 or 4 seconds, maybe 10 frames a second or whatever it is. And then the buffer gets full and they stop. And then you have to wait for that to empty before you can go again. So this is why it's important to get the orbital elements and the timing updated along with the latency information so that if you have a 3-second burst, you want to press the button on your camera, or I would use an intervalometer, a second before it transits. This is especially tricky in the daytime when you can't see the ISS. But if you look at the prediction here from heavens above, it shows you the path, and these may update a little bit the times. I don't think you're going to notice much of a change here because it's probably just going to be a few seconds until that updates till it crosses tomorrow. But you see the magnitude changes greatly. Since it's going to be bright, it's going to be hard to see this. But right when it's near the top, it'll be probably bright enough, so you might have a bit of a clue when to hit your start button. All right, so we'll go back to the other method now. Let's see. And you can use, here's another chart of where it's going to be if you want a more exact location. This is an app you can download for your phone. It's called ISS Transit Prediction. That's for Android. I'm sure there's one, or I assume there's one for Apple, but I don't know what it's called. But it's handy to have this when you're there. There's also going to be a solar transit next week. This is going to be interesting because this transit will actually last a few seconds, probably 3 seconds or 4 seconds. It's very rare that we have so many transits so close to each other. But anyway, especially in the same area here. So you guys that live around here, you have an opportunity to do this. Now, the one thing with the sun, obviously you need a solar filter. But you know, also alignment matters. But the thing is, it's going to be really small. So if you can, the more accurately you can have your camera your mount aligned, then you might be able to zoom in tightly if you're lucky and get it. All right. So the last thing I wanted to show you here was this software. Hold on a minute. I'll share my observatory desktop. All right, there we go. There's the moon. This is a live image of the moon right now. The software I'm using is called Backyard EOS. It's connected to my Canon EOS Rebel 1000D. This software is relatively inexpensive. It's like 20 or 30 bucks, and I think there's a free trial version. But at any rate, the way I would attempt this, if you have a longer focal length lens, and you know, on a mount, you can use this tool. If you switch to planetary mode here, and I'm waiting for it to pop up. My computer's slow. There we go. So if you switch to planetary mode and set your camera to, you want the exposure to be as quickly as possible to stop the motion. So with this particular piece of software, I'm watching a live video here of the camera, but this is not at the full resolution of my sensor. This is, I think it's binning the pixels 5x5. So that's no good. You're not going to get any real resolution with that. However, if you click the 5x digital zoom, now it uses the entire sensor. And every one of these pixels here, one pixel here will be one pixel on your image. Whereas opposed, the other one, 25 to, you know, pixels to 5. So if you have a shorter focal length, when you add this 5x zoom, boom, all of a sudden now you can get the moon to fill up your entire screen. In this case, the moon is more than full because my focal length is too long on the telescope. But anyway, this is the way to do it, because now you can set the exposure, and if you set it to do, I don't know how many frames you want to set it. Time isn't as critical with this particular method, especially if you're aligned either to the moon or to the sun, because now we can take continuous video, and if we just hit the button here, record, we're going to see here how many frames per second we're getting. So that's actually kind of a low number, but it's more than enough, 12 frames per second, especially if you're not zoomed in with a 1400 millimeter telescope. If you put this on a 300 millimeter lens, the moon should fit perfectly into the field. So all you have to do is make sure you're on the moon within a minute, 2 minutes of the ISS transit. As long as the moon's in the field, you'll get it. So easy enough. The problem though, this method can't be used with a Nikon camera. I'm not sure what other cameras are compatible. A lot of Canons are, because they can 1-to-1 pixel ratio when you're at 5x zoom. That's the most important part. All right. So anybody have any questions?
Lou, I have a comment just based on having done this.
Oh, great.
So one thing with the timing, regardless of whether you do burst mode or video mode, one of the most important things is to, as you mentioned, synchronize your watch, basically, if it's your phone or whatever you're using as your timekeeping device to the event. And then even more so, or maybe not more so, but as important, is to trust it. If you wait to see if you're gonna wait to see if it passes or something before you hit that shutter button, you will never catch it. So the times that I've done it successfully, I just keep my fingers crossed. I look at my clock, and I know that I have the most recent orbital elements, and I press the shutter button. I do it in burst mode. because in burst mode, I can shoot at the full resolution of the camera. And I actually found that I get, higher resolution, because when you're doing the uncompressed video, you're basically or not uncompressed video, but the 1:1 pixel video, you're actually capturing, you're actually only using a portion of the sensor.
Right.
So your effective resolution is less, and you might not see as much detail in the ISS.
Yeah, I was offering that option.
I also, I'm sorry, Lou, go ahead.
I was suggesting that to give people an opportunity that don't have a telescope, that may think that they might not be able to capture this. But that 5x.
Oh, right, yeah, but you can just do it with a telephoto lens. I actually don't track when I do it.
Really?
Yeah, I do not have a tracking mount when I do it. I found because you're only sensing, you're only shooting for about half a second or one, like if your burst mode lasts 2 seconds or something, that's all you need to record for.
Right.
So at that point, if you're pointed towards the sun or the moon, you're not going to drift. So what I do is I actually make sure that I am aimed right at the sun. I actually or the moon. I actually use live view, so I'm constantly just centered on that, and I'm watching my clock, and then like a second before I know it's going to happen, I press the release button and I just shoot at high speed burst mode, and the buffer usually lasts maybe 15 or 20 frames, which is more than enough to catch it. Even if it's 8 or 9 frames, you can usually catch it if you're in that 1 second. I've been successful each time. I think I missed one time because I just kind of got messed up. I had the time wrong or something, but I forget what the reason was. But there was one time where I came home sort of empty-handed after trying this.
I suppose if you sneeze at the wrong time, you'll miss it.
Yeah. Do not wait to see it.
Well, we have a guest speaker tonight. Lou, thank you very much. I hope folks are able to catch this. And if you have questions for Lou or for Gary after the meeting, we all stick around, and there'll be time to chat. So at this point, I'm going to, thanks again, Lou. I'm going to throw the meeting to Jeremy, and he will introduce our guest. Take it away.
All right. First, John, are you out there? Ready to go?
I should be coming through.
All right. We got you.
Just a second.
Okay.
Let me make sure my cameras are all started and on. Here we go.
All right. There you
Hi.
are. All right. So if you are not the speaker, we ask that you mute your audio and turn off video. And if possible, please hold questions to the end. If you need to ask something, you can always put it into the chat as well, and then I can pass that along. So before we get started, a little sneak preview of some upcoming meetings. In February, we will have Dr. Jolene Carlberg, who is with STSCI, Space Telescope Science Institute. They're the folks that run Hubble. And she'll be talking about ultraviolet astronomy, which is actually a nice complement to what we'll be hearing about this evening. In March, we'll have Dr. Stephanie Lamassa, who is also at STSCI, and she'll be talking about supermassive black holes. And in April, we're going to have Dr. Dan Wertheimer, who is at Berkeley and is associated with SETI, the Search for Extraterrestrial Intelligence. And he's going to talk about the search for extraterrestrial intelligence. Is anybody out there? All right, so tonight, we're very happy to have back John Conrad, who is a NASA JPL Solar System Ambassador. He's a good friend of DVAA. He's given us several presentations in recent years, including global climate change, the view from space, lunar science, and some presentations about solar system exploration. So John's background is in astronautics and space flight, and he's worked in unmanned space programs for the Air Force and for NASA, and he's worked in various areas, including aerospace, defense, IT, energy, and security programs. So we're very happy to have John back here in this virtual format. So we don't get to see him in person, but he's back here tonight, and he's going to tell us about NASA's infrared platforms seeing across space and time. So please join me in welcoming John Conrad. John, take
Hi,
it away.
everybody. So you see me all right, Jeremy?
Yeah, you're good.
And I guess if you've transferred it over, I can share the screen then. See if we got that. You see this?
Yeah, we're good.
All right. And I'm going to turn my camera off here so I don't distract you. Let's see. You should be looking at a familiar nebula. Is that correct? Can you all hear me?
Yeah, I can hear you.
Yes, sir.
Okay. So you should be looking at a familiar nebula, the Horsehead. We all love this one. And I thought I'd just start off with a couple quick videos as the flavor of the talk tonight, which is to talk about the utility of the infrared band of the spectrum. So we're looking at one of our favorite constellations here. There's the Belt of Orion. And as we continue to zoom in here, you see the wonderful nebula in the molecular cloud near the left-hand star of Orion. And this video done by NASA and the Space Telescope Science Institute for the 23rd anniversary, which would have been in 2013, is just fantastic. And what it does, it shows you very graphically and quickly the value of going up into the infrared part of the spectrum as opposed to what we're used to seeing with a dark nebula and all the cloudy hydrogen gas around it. And now going from the visible into the infrared, you get to see the wonderful benefit of moving up to longer wavelengths, seeing through clouds. In the case of the Horsehead, you're seeing actually into a very dense cloud in a star forming region. And so it's an extremely valuable part of the spectrum. We'll be talking about that more. And so with that, let me move on to the next slide. And the next slide, hopefully we can get there. Okay. Murphy is doing his best here. So the next slide you should recognize if you've taken a minute to take what was put into the email as a just released, you see down there, January 2021 by NASA and STSCI video to illustrate the value of looking through Hubble's visible and infrared to get a really deep look, which is the other thing that's a great benefit of the infrared part of the spectrum. And so what we're looking at here near Orion is an area that as we zoom in with Hubble continues to be just filled with stars, deeper and deeper, until we finally get to an area that's about the size of a grain of sand held at arm's length. That's a very small field of view, and we haven't gotten there yet. And Hubble stared there. And picture a low Earth orbiting satellite, which Hubble is, having to open and close the sun shield with 1.5 hour orbits, and yet they were able to stare and stare deeply for 11 days when they added it all together and give us this wonderful ultra deep field. And within that ultra deep field is almost all galaxies. It's just phenomenal. There are a few stars. They're being plucked out here, but if you follow through on the video, which I won't, what you'll find is that it goes through and shows different galaxies and their forms at different epochs, different times of look back through the universe. And so we're going to be talking about that and how it works tonight. And so hopefully this will move on now. So as I've said, infrared, NASA has some great platforms to view in the infrared. And once again, we at NASA appreciate the opportunity to bring this information to you folks. And I'm just delighted to be back. And so what you're looking at, maybe surprisingly, is the best available infrared telescope that NASA has right now, not in space, but like a few other dozen platforms mounted on aircraft or drones. And in this case, it's NASA's largest observatory, and we're going to talk quite a bit about it in a few minutes. You may recognize 747 from a very familiar look at a 747 just a couple days ago leaving Washington. So we'll talk about that platform. We'll also talk about the space platforms that NASA has with capability for the infrared, with the Hubble in the middle and the upcoming, applause, applause, James Webb. Everybody is excited with this coming. The simple graphic I've shown here is to give people like me that are lay people, not astrophysicists or maybe not even physicists, the opportunity to think a little bit about the spectrum in a very high level sense. And so we go through the wavelengths as they get from radio, which is very long. Radio waves can be a kilometer or so. And as we move to the right, the waves are closer and closer together until we get to the middle there, the visible, which is named that simply because human beings have receptors for photons, and they're only sensible in this band that we have labeled the visible band. And as we go shorter from there through the ultraviolet, we eventually get out to the highest energy part of the spectrum, the very high frequency and very short wavelength X-ray and gamma rays. And the reason I wanted you to see it this way was to think about what's called redshift, and think about the factor that if you're viewing something that is at any point on the spectrum, and you're viewing it at a certain point in the universe, maybe a billion years ago, the source will give off photons in a certain wavelength, but those photons, as they travel through the universe, maybe to the Earth for us to view, may take, billions of years. And during that time, we now understand that space essentially expands. And as space expands, it stretches waves. And so something that originates as a source in the ultraviolet will actually stretch in wavelength over the billions of years until it moves to where it's no longer visible in the ultraviolet, but it is in the visible, and then eventually in the infrared and so on. And so the look back time, which is tied to this red shift, the shift toward the red, is correlated to the age of the universe. And we're going to use that as we'll illustrate later. But another feature of infrared, which you see is at longer waves than the visible, is that the longer wavelengths, and you can kind of physically picture this, as long waves come through a medium that's got a certain density of particles, say it's the atmosphere. And so it's got aerosols and water vapor and various kinds of scatters, dust, and so on, with a certain density. As you come through that dense cloud of scatters, the longer waves are able to pass through more easily because they miss a lot of that. But the shorter the waves are, the more they get caught up in the density of the scatters and get bounced around as you move towards the right with more scattering. And that, among other things, is the reason why the sky is blue in the daytime. At any rate, I want to point out then that infrared does see in a certain way, which you wouldn't simply say is better, it's just different. And so it's different in the sense that because of this scattering phenomenon, allows us to see better through the dust and water vapor of the atmosphere. And so we'll take a look at how that works on another graphic of seeing through the atmosphere. So in their inimitable style, they've given me a slide that flips the directions for the spectrum. So now the long waves are toward the right and the short waves are toward the left. And the colors of these stripes coming down from space as you come down in altitude to the bottom, which is the Earth's surface, And you see that for the very highest points where we like to put our telescopes, so they're above some of the scattering atmosphere, you have some of these wavelengths, especially in the visible, you see right there in the middle, but also some of them towards the right, towards the longer infrared, and a few towards the left in the ultraviolet. But you can't get very far in either direction before the waves no longer can pass through the atmosphere. And so you see where that, I've talked to you about a telescope on the mountaintop. Now, if we go up more than double that altitude to an aircraft, like the one we're going to talk about, now we have a place where you're at an altitude and it's high enough above a lot of the scattering atmosphere that a lot of the infrared does get down to that altitude. And that's what we're going to be taking advantage of today as we talk about that platform. Another way to look at it, if Mauna Kea is that ground-based observatory on the top, as you look at the spectrum from left to right, going from 1 micron, which is actually longer wave than the visible, so the visible is actually off the chart to the left. If you go from 1, which is near infrared, through 10, which kind of gets out to the middle infrared, over to 100, which is far infrared, then that sky blue in Mauna Kea indicates that the atmosphere is opaque at those wavelengths and you can't see things there. And it takes until you get out to the millimeter area, 1,000 microns, where we have a nice array down in Atacama in the desert in South America, which is able to see the millimeter wave because there is transmission there. But you contrast the upper, which is an Earth-based telescope, to SOFIA, which is this airborne platform, and you see that there are many holes, and in fact, mostly transparency through the middle and well through the far infrared, and we'll see how that helps us. So simply speaking, there are some special advantages, things we can't see in the visible frequencies or visible wavelengths that you can see in infrared that are very handy. As you know, you can go out at night and the eyes are very sensitive to stars, which are very hot, and our typical observatories and many of Hubble's best pictures are looking in that part of the wavelength and seeing nice representations. But if you go to a cooler part, and cooler as in formation of stars, as opposed to actually to after the stars light up as stars, that star forming area where planets are also being formed is quite a bit cooler. And so we get the advantage with infrared that we can see cooler things in the infrared. We also, as I mentioned, or showed you actually with the Horsehead, can see through a lot of the interstellar dust clouds and within some of the thick ones to see the star formation. And finally, not talked about a lot is the fact that the spectral signature of some of the life-oriented molecules, organic molecules, biogenic molecules, are very strong signatures in the infrared, and so it's easier for us to look for signs of life in that part of the spectrum. And then because we're talking about an aircraft, we have an advantage from being a mobile observatory, which is to do things that probably all of you are familiar with called occultation observations, where we get a favorable geometry and once in a while from our driveway or backyard or from one of the fixed observatories around the world, you get just the right geometry to see certain stars pass behind solar system bodies, whether it's the moon or a planet, some kind of a disk. And you can take advantage of certain special measurements or just the fact that you get to see a star blink out and come back on. And that's fine if you happen to be conveniently in the right geometry, but with a mobile observatory, you get to fly wherever you want and set up your flight plan and do these things in a really well-planned way. And I'll give you a good example of that soon. So here we have SOFIA. The I in the acronym stands for infrared. It was designed and built for that purpose. It was it was a 747 purchased by NASA with a 100-inch diameter telescope mounted, as you can see, through a door that opens and closes there on the side of the aircraft. And we'll show you a little bit more about that in a minute. But one of the unique things about this photo is the doors open during the daytime, which once you have the primary mirror in there, you don't do. They don't fly during the daytime typically. Another aspect of the 747 is where it's based. You may have heard of NASA Armstrong. You've almost certainly heard of the Air Force Base where it is, which is Edwards, where the shuttle landed, where most of the early astronauts, especially who were test pilots, got their training. And so one of those astronauts, Neil Armstrong, got to attach his name to the NASA facility that's co-located there at Edwards in Southern California. That's where the plane flies out of. The people that manage and perform the research and mission operations are based out of another NASA center up in the Bay Area, NASA Ames. And you may be able to make out the other logo on the tail, which is DLR, which is the German for the German Space Agency, because they in fact have put one out of every $5 into the development and outfitting and operation of this system since the beginning. So they're a major partner for us. It flew for the first time in 2010. It had actually been purchased about 10 years before then, and it took a while to set it up and get the instruments ready and everything. So 10 years ago, last month actually, was the first flight, and we're going to see one of the results in a few minutes. In a typical year, it flies on an average of every 3 days, all night, 8-hour science gathering flights. And the other feature of the operation is that, as you guys understand, you don't get to see the whole sky flying out of base in the Northern Hemisphere. And so they have a base in New Zealand, the same base and the same flight line and everything that's used for the flights that outfit the Antarctica teams. And so during the winter time in Antarctica, they don't fly much out of there. And so NASA goes there in the summertime up here and spends a week or two flying out of there to get the perspective of the other half of the universe. The 3 parts, you can kind of guess what they are, the big pieces of this whole thing. One's the aircraft, as I mentioned, a special 747. It was built and flown, I think, in the 70s and 80s and into the 90s by United as a regular airliner, and then purchased by NASA and outfitted and completely changed around to become the Sophia platform. Flies at a bit more than twice the height of the highest Earth-based observatories and well above a bunch of the atmosphere. The second big chunk is the telescope, and it's a reflector like many of us have. And anybody that ever complained about lugging their big Dobsonian around or something can think about a 37,000-pound telescope, which is what this is that's mounted there in the aft part of the aircraft. And finally, the business end of their research is done by a set of very special, specially designed instruments that you'll get to see here in a minute. And so let's take a quick look at how the thing is outfitted with this cutaway. We'll start towards the aft end, the right side, and you see there the telescope mounted looking through an opening, which is in fact an open cavity. It's not glass or any kind of material. It's just looking out into space. And because of that, as you can imagine, at 40,000 feet, with the temperatures and pressures up there, you need to do something so you can be on the aircraft with it. And so that green thing there is a pressure bulkhead. that allows the uninhabited part where the telescope is to work just fine, and people to work in their shirt sleeves up here in the front, with areas for the mission controllers and even observers. There are plenty of educational parties that get to travel on board. And there's an open area here that gets filled up with the science instrumentation. I wanted you to get a better feeling for that door. The door, in fact, is, I believe, about 14 by 18 feet. And it is part of a beefed up circular cylindrical portion of the aft part of the 747, which you'll see here. So you see that bulbous part behind the wing. And this is a daytime flight. It was very early, and they were actually testing. This was a test to see what kind of buffeting, what kind of airflow, what kind of disturbances to the telescope there might be from having this wide open door. And they had an experiment, and the PI is the one that gave us these slides and talked to us. And he said on the way to this this flight, they went to Home Depot and bought a couple rolls of twine and a couple rolls of masking tape, and they cut them and pasted them all around. They're hard to see here, but that was their experiment to see what kind of airflow there was around this opening. And it turned out to give them great results. There is, in fact, as you'd hope aerodynamically, laminar flow, smooth flow across the opening. So there's literally no disturbance inside, even though that side of the aircraft is wide open. So there you saw it open. Now you're seeing it close, and I'll move on. Here's a look at how the telescope works, with a star providing its light to the mirror, back up to the secondary. And then in this case, we've got two tertiary mirrors. And I'll go through that again so you can watch that. We'll start with the starlight down to the primary, the way we're all familiar with, up to the secondary, and then not one but two tertiaries, with the light beam being separated spectrally by a dichroic filter. And most of the value is in the infrared instruments that you get access through that light tube. But there's also a visible wavelength camera that's helps with positioning and photometry and so on. Now let's see what it actually looks like physically. And unlike in the aircraft picture, in this case, we've got the primary mirror in place. We have, toward the far upper left there, you can see part of that pressure bulkhead, and you can see this very strong bracket system that holds the telescope. And I wanted you to see these two things, two optical cameras that view the star field all around the target area and give you the ability for extremely precise and accurate stellar observations and measurements. And so another view of that same area, this one with a cutaway to show you actually how that telescope is held in a stable way and also able to be precisely pointed. And once again, you see the arrows pointing at those optical TV cameras, but note the bulkhead. And as the arm or the light tube of the telescope comes through the bulkhead there, it's sitting on a spherical bearing. And this bearing, which you can kind of make out the spherical shape of, is actually two concentric spheres. The inside one's attached to the telescope and allows it to move. The outside one, which is just slightly larger than the inside sphere, is separated by a high pressure hydraulic fluid layer that allows, and it's fixed to the bulkhead so that the inner bearing can float. And so it's got gyroscopes to, keep it stable, and these TV cameras to help with the pointing. All right, so here we have that, the payoff of the missions, where the data is captured in one of 6 different, I was going to call them experiments, but they're instruments. They've been used for many, many years. Each of them is large enough that it can only fly by itself. They mount onto the blue area there. You can see is in the forward part of the cabin where the light tube comes through. And so that's where the infrared comes. 5 of them are sensitive in the mid, and I'm sorry, 2 of them sensitive in the mid, 3 sensitive in the far IR. And of course, the other one, FPI plus, is that visible wavelength instrument as well. These are quite large and heavy, 1,000 pounds each, give or take a couple 100 pounds maybe. And only one is flown at a time. They take about a day to change in and out. So here's now a look on the spectrum of what the coverage is spectrally and what kind of resolving power there is in terms of resolution up the vertical axis. And so the 5 that are currently used all the time, the 2 mid-IR, X's in green and forecast in pink there. And then as you get out into the mid part of the picture and the mid part of or the far part of the IR spectrum, you have at the top there something called great, and then in yellow, Fifi, and the bottom with turquoise or green there is hawk. And that's the sweet spot. And I call it that because from 30 to 300 microns is the definition of far infrared. And at this point, there is no major observatory other than SOFIA that has really advanced instrumentation to view and get good views through the transparent atmosphere because of their altitude. The NASA infrared telescope, Spitzer, is no longer operating. And so this is the best that we have, and it does a great job for the time being. You can see a couple other colors, blue and you know, brown or whatever that is there, red. Those are instruments coming along in the future, reaching well out past the far infrared, even into the millimeter range. And you see ALMA, the Atacama millimeter array in South America up there for reference. All right, and finally, just to give you a picture of how this all works for these 8-hour flights. Guy's got a t-shirt on, so I guess that pressure bulkhead and the heaters work pretty well. He's in the instrument section operating the instrument. The mid-ground there has probably got the mission controllers with their displays, and in the near with their backs to us are just some observers. And I don't know about you, but I would love to go on one of these nighttime missions at some time. All right, so now what have we gotten out of SOFIA in those 10 years? And so the first thing we're going to do is take a look at something on Jupiter. You're all familiar with this. I think this is one of the many Hubble images. But at any rate, you recognize that dark band in the southern hemisphere. And it has been understood for quite a while that what we have there is organic material, hydrocarbons and that sort of thing. And that's in the visible. And when you add to that, as we did on the very first mission, a year ago, last month was flown, and they flew it and they used the instrument that gave them viewing in those 3 infrared filter wavelengths that you see at the top there. And what it did was give them a striking example of what additional information you get, because not only do we know now that that stripe is special material and different from the surrounding stuff, but also there's more heat being emitted from that band than anywhere else on the orb. And this goes along with the fact that an earlier NASA aircraft observatory flight, not SOFIA, had come up with a finding that had been confirmed for both Jupiter and Saturn, that the amount of heat or energy that is released by those 2 gas giants is greater than the amount that is received from the sun. So they know that there are positive energy producing activities going on in the atmosphere. And now we know and can show where the lion's share of that heat is escaping in that band. Another use of SOFIA, as I mentioned, was for occultations. And so I think many people in the audience, maybe all of you, are familiar with how the light is seen as you watch a star pass behind an occulting object, some kind of a disk. Maybe it's the moon, maybe it's a planet. In this case, it was Pluto. And so you go from the left there, where the magnitude of energy you're seeing is the sum of the star and the disk energy. And then you pass behind, the star passes behind the disk, and you quickly have only the light of the foreground object, in this case, the planet Pluto that you're observing. And then on the far left or the far right, you come back up when the star comes back out and you add that energy back in again. And you have the opportunity, if there's an atmosphere on the occulting disk, to take advantage, if you have a good geometry, of the starlight when you're perfectly aligned, and that starlight is able to be integrated as it comes around through the atmosphere, and that's what that peak is that you see in the center there. So they flew a flight plan carefully and precisely designed and flown so that they got this peak perfectly and got the maximum amount of light from the star through the atmosphere. And what's particularly interesting is they'd done the same flight 4 years earlier in 2011, and they were able to observe that the peak was quite different in the two different flights. And that led to their theory, their suggestion, that there might be some kind of active process on Pluto that was providing energy into the atmosphere other than just what they were seeing with the light. And so it turned out that that finding was provided several weeks before New Horizons arrived there in 2015. So they kind of scooped New Horizons in one way. And New Horizons, as you're probably well aware, took not just wonderful images, but was able to analyze them and find cryovolcanoes and other sources of geologic activity that are very evident on Pluto that we hadn't necessarily expected to find. Here we have a Hubble view of one of our favorite kinds of objects, those of us that like to look through eyepieces. And you may or may not understand planetary nebula. I understand them a little bit to be effectively the late stages of a star in its evolution, when it sloughs off and ejects layers of material of different elements and molecules off into space at very great velocity. And so we get a chance to look at these sort of spherical emissions, as sometimes they overtake each other and intersect and so on, and give us wonderful displays with the stars still in the center from time to time, like every million years or so, maybe emitting off some more. But at any rate, this is all about the fact that we looked at the chemistry of this particular nebula, NGC 7027, and found something that the astronomers had been looking for, especially the cosmologists, because what they found was evidence of a really special molecule in the field or in the layers of that nebula. And you may or may not be able to kind of make out what this artist's picture of a molecule is, but what you have there is helium and hydrogen, which were the two earliest, hydrogen first and then helium, which was formed rapidly from the hydrogen and then fixed in terms of amount early in the universe's history. And forever after, we have about 3 times by mass as much hydrogen as helium. And what the cosmologists had figured out was they thought that the conditions of heat and pressure would have been such that the first molecule formed would have been an unusual one, not H2, but H, hydrogen, and helium forming the molecule helium hydride, a very rare molecule, I'm told. at any rate, it turns out that just recently, I think this was in late 2019, Sophia flew and did the spectroscopy that gave this very precise spectrum in the infrared that shows in the gray there in the lower right. It just nailed the helium hydride molecule for the first time that it's been confirmed in the universe. Now, that's not saying these are molecules from the early universe. It's just saying that we have now confirmed that it is out there, as had been theorized. So finally, this one's probably my favorite, looking towards the center of our galaxy. And you've all heard, we've perhaps read a lot about the findings of the black hole that is at the center of our galaxy. And yet with our best space telescope, Hubble, it doesn't see far enough to be able to block out see through the central star cluster. And so this is the best that Hubble has been able to do. And yet Sophia has looked at it further out into the infrared and given us this amazing image. Very, very high resolution image of the black hole at the center of the Milky Way. You see that torus there. And in addition to the cloud of matter that kind of clumps up around that gravitational hole, you see at times there are chunks of that get sucked down the throat of it. And I just think it's an amazing picture. All right, so that was our airborne platform. Now we're gonna talk a little bit about how we're able to see deep, which we can particularly with our space telescopes because they can stare at the same thing very precisely for a very long time. Here's Hubble in the context of the age of the universe. Hubble's over there at the left, which is today, looking deep in look back time, if you will, back towards the beginnings of the universe 13.8 billion years ago. And so Hubble, as we used it to stare and come up with deep fields, we first got the Hubble Deep Field, you see labeled there at the bottom, HDF. And I think they got that somewhere around 20 years ago. At any rate, after staring a lot, they were able to publish that particular field filled with galaxies, and were able to figure out from the redshift of the galaxies, and you see there 5.5, and I'll talk about that in a minute, means that they were seeing things where the source light had come as long ago as over 13 billion, or about 13 billion of those 13 billion years. In other words, at a time, back through time to only a billion years after the Big Bang. And then they worked harder with different instruments to stare even longer. And that's the video that you saw back there in the beginning that each of you have the link to, I think, from Jeremy. And with that, they were able to look at the Hubble Ultra Deep Field and find several very, very distant, very, very ancient galaxies, and conclude that this record holder, GNZ11, where GN is Goods North, which is a particular selected very dark area of the sky that they've done lots of looking in. And with looking for the integrated sum of 11 days through the infrared eyes, where Hubble looks into the near infrared, they were able to image this particular very old galaxy, estimated to be about 400 million years after the Big Bang. I don't think anybody ever imagined 25 years ago that we'd be able to see that far back with the telescope that we launched in 1990. Anyway, so that's what's been achieved so far. And I thought you might be interested because many of you may be very much lay people like I am when it comes to certain areas of physics and astrophysics. And so here's a fairly simple animation that NASA put together to help us to understand what redshift is and how it works. So first of all, across the middle of the bottom there, you see UV, visible, and near infrared. So from left to right, we're looking at the spectral bands that increase in the wavelength. And so as things move from visible to near infrared, we call them being red shifted. The wavelength has been shifted toward the red and eventually will be shifted beyond the near infrared to other regions and even beyond that, if there's enough redshift. And redshift happens because photons are emitted at their own wavelengths. And I'll just ask you to look for a second at the left hand. Didn't want to do that. Let me come back out and do this one again. So if you look at the left edge there, you will see something that's called the Lyman break, and it doesn't matter why, but it's got to do with the fact that the integrated photons, light from distant galaxies, have a place at the left, which is towards the shorter wavelengths, where no more energy is received as you move further to the left. And so there's kind of this sharp cliff on a spectrum. And the spectrum of a distant galaxy is what that cloud of gray is there through the middle. It emits across all of those regions, from UV through visible through near infrared. And what you see across the middle are filters that Hubble had. F435 means 0.435 microns, which is down in the ultraviolet and blue area. And you move to the right to longer wavelengths and pass the frequencies or the wavelengths there, and you move through the visible all the way over to the right. F160 is 1.6 microns, which is in the near infrared. So Hubble, with these 9 filters, if there happens to be a galaxy that you're seeing that's up close and the cutoff starts over here in the ultraviolet on the left, then you actually get an image through each of those 9 filters that's shown at the bottom there. And so you can image those. Now, what redshift does is cause the light all to move to the right, to the longer wavelengths toward the red, as the universe expands. And so after 2 billion or 4 billion or 6 billion years, the universe has been expanding, and the photons that started over here at roughly 0.1, which is where the Lyman break is, will have moved and been stretched through space well over as time passes, as the distance of the galaxy is further and further away. So for example, here, whoop, it's always a little tricky to make this work, sorry. So we're just trying to stop here at about 5.5. That's where the light is from a distant galaxy. And so when we said in the Hubble Deep Field that we could see back to 5.5, the galaxies we're seeing were able to fill the spectrum, having been redshifted from about the middle over to the right, but the cutoff has made it so that they aren't very visible anymore in the shorter wavelength areas. And if you move yet further, we'll just let it run out to where the Hubble Ultra Deep Field has found some galaxies, then the initial 0.1 micron wavelength over there at the left has been redshifted through the expansion of space over about 13.4 billion years, to where that light now is a signature over here in the near infrared. And so what you can see quickly then perhaps is, since this is the limit of Hubble's viewing, is that anything further back than that with a higher redshift won't be accessible to Hubble. So we need a new capability. And so here's that capability. The Webb or James Webb Space Telescope was specifically designed to be an infrared telescope for exactly the reason that the light from the deepest things is not accessible in the ultraviolet or visible, and not even the near infrared. You need to look back further. And so we anticipate, if we're right, that we will be able, with the instruments on Webb, to be able to see back almost 99% of the way back to the Big Bang. It's just amazing. To the first galaxies, almost certainly, and hopefully even back towards some of the first stars when literally the universe had first light. So let's cover pretty quickly here the overview of the two telescopes. Hubble you're familiar with, the James Webb you may be familiar is much bigger, about 5 or 6 times as much collecting area for all the light, 25 square meters. And the other big difference we've been talking about is it's mainly an infrared telescope. And in order to be a good infrared telescope, the temperature of the detectors matters. It turns out in the case of Hubble, we are able to operate just fine, essentially at room temperature. But you may know from infrared cameras and such things that you get best results in the infrared if you have cooling. And so very great cooling is required in order to get the best results with your detectors. And that's what they're going to have with the Webb. 40 Kelvin equates to, or can be compared to, I said 70 Fahrenheit, but 70 Fahrenheit's about 294 Kelvin, I think. So this is much, much colder than the Hubble was. And in fact, the whole instrument package, everything on the away from the sun side, those blue layers are a sun shield. And so the sun will always be blocked from all of the telescope and all of the instrumentation. Here is a picture, because I like people to have a physical feeling for things. In the clean room, when it was all put together, the segmented telescope, the primary there, you see 25 square meters, and you get an idea from the guy standing underneath it there of just how big that is. And the secondary, of course, sticking up. When you put it together, you have to fold it up in order to fit it into a spacecraft. And so the fairing requires you to fold back what they call wings, segments of the primary, and fold up the secondary there, and then actually roll up in a very special way the sun shields that will be unfurled underneath that. The mirror itself, I imagine you guys would be interested in. It's not just big, but it's segmented. And I am kind of impressed with the fact that each of these segments, which is about 50 inches across, only weighs about 80 pounds. They're made of beryllium, chosen because there's literally no expansion or contraction in the region of operation. And they are layered with the best, most reflective kind of material, gold, 98% reflection. And especially important, since it's 18 different segments, is to get the shape right. And the way they do that is amazing, I think. Each of the segments has got 7 actuators. 6 of them account for tipping and tilting it so that it's just right in a macro sense in relation to the other 17. And so you form the gross shape of the parabola that way, but they might be slightly out of curvature. And so there's an actuator on the back of each of these, and the segment's flexible enough that they can actually change the curvature. And so a lot of the early preparation, once they're out in space for first light, will be to get the best possible shape that they can with these apertures, or with these actuators. So here it is, not yet flying on the vehicle, but this is the vehicle that will fly it. And you may or may not recognize the European Ariane 5, a big booster. It's been very successful for many missions. You see ESA, European Space Agency, on the side of the launch tower, because NASA contracted with the Europeans for the booster and for the launch site. And one of the last of this big booster class, the Ariane 5, maybe the last one, will be the one used to launch Webb. French Guiana is the reason NASA's going there. It's on the east coast of South America, very close to the equator. And so for a large payload, you get the absolute most benefit of the Earth's rotation by launching to the east from there. And so they'll be down there. later this year, and we have our fingers and everything else crossed that it'll get off on schedule in October. The sigh of relief that I used to get to give out, within an hour or two of launching low Earth orbiting various kinds of NASA and military satellites is not going to be achieved for a very long time for the people responsible for this mission. Not only will they have to wait a while until this thing goes up into Earth orbit and then starts off onto its long voyage across to the second Lagrange point, but it takes a very long time to get out there. And so it's going to take a month before the payload, the Webb, will even be on station. And by on station, I'm just going to remind you here, I think we've talked about Lagrange points. Every two-body system has a mathematical solution that has 5 theoretically stable points, and it turns out now that we're flying spacecraft, it works very well. The L2, the second Lagrange point, is in line with the two bodies, the sun going through the Earth and then beyond, 1/10 of the distance between the Earth and the sun, which is 1.5 million kilometers, almost 1 million miles further out. And so that's the point at which you're going to place the spacecraft. But exposure to the sun is really important. And the last thing you want is to have the spacecraft, even if you think you can precisely control its position out there, and it is stable and doesn't need much control because it's at a Lagrange point. But the last thing you want is for the Earth's shadow to sometimes be cast on the telescope and sometimes not, because expansion and contraction are terrible enemies of everything in terms of actual precision of pointing and so on. So what they have is what's called a halo orbit. So once it gets out there, it will actually swoop out of the line into a circular orbit that's actually quite wide, quite far away from, but orbiting in a circular orbit around that Lagrange point. And by doing this, you can turn the sun shield, as that little cartoon indicates, towards the sun, and it stays there forever. You don't have to think anything about opening and closing a sunshade. You can stare when you can get the geometry right as the Earth goes around the sun through the years, and you can, control the pointing of the spacecraft or the telescope in other ways, but never do you have to worry about the sun being in the field of view with those sun shields. So that's a month in when you get out there and get into orbit, and then there's even more time. It turns out it takes quite a while to cool down to 40 degrees Kelvin, get everything cooled down. They think at about 2 months, it'll be cooled down enough that they can start to test some of the instruments. And they're projecting that maybe a little bit before 4 months after launch, they will actually be able to have the configuration of the 18 segments and the exact shaping of them, as well as the testing of the instruments ready for first light for certified operations. So that's going to be a very, very long and exciting time to anticipate, hopefully, success with a launch late this year. We're talking about maybe having some of the first really good pictures early next year, but maybe not until well into the year, and hopefully it'll all go well. And when I say all go well, you'll see in a few minutes what they're planning to do right away. 4 instruments designed, selected and designed quite a while ago. The little rectangles indicate who did them. The 2 on the right are European. The upper left is an American one, and the lower left is a Canadian one. 3 of them in the near infrared, and they work fine at that 40 Kelvin. But the mid infrared, in order to get the detectivity out there that you want, you have to go to 6 degrees Kelvin, almost absolute zero. Active cryo cooling will be used in order to get down to that temperature and be able to see the best in that part of the spectrum. The other interesting thing I'll mention about these 4 that I really like is this lower right one is called the near spec, or the near infrared spectrograph. And imagine the field of view that you're going to be seeing, and imagine trying to get spectra of individual objects in that. And so what they've designed, and they've actually flown this and used it, it's a physical metal array with magnetization that allows you to command and open and close little tiny shutters, a matrix of shutters, and plan out for where you're pointed exactly which stars you want to have come through while you're doing an observation. And up to 100 individual stellar spectra can be collected during a staring time with this micro shutter array. All right, so the goals, you can almost guess some of the goals now. Since we can see well out beyond where Hubble is seen in the infrared into the mid-infrared, we're hoping to see back into the first couple 100 million years, which means maybe back to the end of the Dark Ages. And, you know, wouldn't it be amazing if we could actually see kind of first light in the universe? Another thing, because we'll be able to observe galaxies at all ages and in all sizes and shapes, we'll be able to start to confirm things about the theories of how galaxies evolve, what shapes they are in various times of their life, how long it takes to form a spiral, things of that nature. The resolution with 5 or 6 times as much light gathering capability compared to the Hubble views that you see here of protoplanetary systems will hopefully allow us to see lots and lots in these protoplanetary disks as far as the formation of gases being collected into lanes around the central star and perhaps forming into planets and maybe even seeing those planets. And as I say that, one of the final objectives is to try to use that feature of the part of the spectrum for life-based molecular spectra that we'll be able to collect and learn more about planetary systems and the origins of life. So this is straight from the NASA astronomers. They wanted you to understand what it feels like to be waiting for this. And so they gave us this video. And I hope you're enjoying it. I can't hear anybody, but I've certainly enjoyed this. And I can't imagine how eager some of these people are, because this was conceived and approved back at the beginning of the millennium. And they had an initial launch date, and it was a serious one, 14 years ago. And so there are people that have literally spent their career preparing for and hoping for this magnificent new telescope, and they're still waiting. So, you know, give them a break if you think they're just, you know, too eager. The fact is, just to confirm how long we've been planning, the Science Working Group, which is composed not just of NASA, but European and Canadian Space Agency personnel, actually solicited the first research investigations 20 years ago. And they did this in order to get an early selection or an early indication, at least, of what kind of instruments and who would need to develop them and what the state of the art might allow and so on. And so literally the planning of the research and the attendant detectors and instruments has been ongoing for 2 decades. And the Cycle 1 program, the early research done by Webb, has promised a bunch of the time, guaranteed a bunch of the time to the people that have been around. There are over 100 of these that you can read about online if you want to. There's another Cycle 1 program that gives the Webb director the discretion, working with the Webb Advisory Committee and the Space Telescope Science Institute, to name, I think they have 12 or 13 specific early release science objectives, and they're to be given priority during the 6-month commissioning period. And so here are a few examples of the guaranteed time observation and early research science you won't be surprised at these few that I've listed. Imaging of exoplanets, boy, are they, I'm excited to see what they're going to be able to see. So far, we've actually imaged one in the, I can't remember what system it is. Seems to me it's in the Alpha Centauri system, but at any rate, but getting much, much more light and much better resolution to be able to see exoplanets next to their stars will be something. Formation of the galaxy, evolution of the various galaxies through the ages, hopefully back as far as reionization, and within our own galaxy, being able to look way, way out at the edges of our galaxy, not just in the halo, but way out at the edges, because the infrared part of the spectrum allows us to see through and see past more occluding stuff, and about 100 other things. And you can read all of these if you want to on that those web pages that I show at the bottom there. So that's it. I appreciate that, and hope that there are some questions, and I'd be happy to try to answer anything. And I guess I'm going to maybe stop sharing here. Anybody there?
John, thanks.
Yes, right here.
John, thanks very much. My first question is, how's your ankle?
Who's asking?
It's Harold.
Oh, well, thank you, Harold. A number of you were very kind to ask, and the rest of you, I'll give just a few details. 13 moons ago, literally, you may remember I talked on lunar science 13 full moons ago, the night, and had a really enjoyable time with you and Radner, and then walked down to the lower parking lot and made the mistake of not walking around to the asphalt part of the entrance, but just the little steep hill there at the bottom. And thankfully, one of your members helped me get up because I destroyed my ankle in a fall and drove myself to Chester County Hospital with no right foot. Spent a terrible night there, had surgery 4 days later, and spent about 3 months essentially on a sofa in our first floor. But I didn't do the work my wife did, as you can imagine. It was just a terrible year. And so I was literally locked down. We were locked down 2 months longer than anybody else this year. So it was 2020 was really a bad year, but I was walking again in some fashion within 4 or 5 months, and now I'm pretty normal.
Good. It's good. Well, it's good to see you here again.
Thanks.
And
Thanks for asking.
be careful. Be careful exiting your computer tonight, for sure.
Yeah, I told Jeremy early when I was getting up that I'd probably trip on the way to the kitchen. So, any questions?
Yes, sir. Mike Tucker here. First of all, excellent talk. I had read quite a bit, I thought, about Sophia on different, probably Sky and Telescope Astronomy magazine or one of the other publications, but your detailed pictures and movies were excellent. Thank you very much. I was going to ask about maintenance on the primary mirror, but the actual instruments really got my attention. How the heck do they get them in and out of the airplane?
Nobody asked that when we talked to the PI. It's an excellent question. I don't know if they have enlarged a door on the other side. I didn't see a larger door on the left side.
Mm-hmm.
It's a good question. Now, they weren't as, they're heavy, but they might be able to be lifted in through a normal aircraft door.
Mm-hmm.
Not sure.
Being the size that they are, I assume that wasn't just a cabin door, for personnel. I'm sure maybe it's the luggage area or something along those lines if they redesigned it. The other thing is that how often do they, I'm assuming the primary mirror is re-illuminized every once in a while. How do they do that? Do you understand the maintenance on the primary mirror?
Michael, I'm going to just tell you, I don't know.
Okay, thank you. That's all right. Do you also know who maintains the aircraft itself? Is it NASA or Boeing?
The way these things go, 10 years into the many missions they're doing, having worked on many larger government programs, it could be them or it could be any third party at this point. My guess is that it's not NASA. NASA we talk about NASA's accomplishments, and I think we're all big boys and girls and understand that most of the things you see that NASA says are theirs were built by people at the company that I work for, Lockheed, or somebody like that.
The different companies, right?
Yeah, but as far as maintaining things go, the price point for that often has companies that you don't even recognize that are doing those sorts of things after things get mature.
Thank you.
That'd be just a guess. Anybody else?
Yeah, I have a question. I'm really curious on how accurately or how precisely the telescope is stabilized. I was really fascinated by the system that you were showing with the concentric, the gyro floating inside. Is there anything attached to that? I mean, is it free floating?
It is free floating. The free floating in the sense that the inner of the two concentric spheres holds the light tube telescope array, that 37,000 pound humongous thing. I've wondered myself how they balance it, to be honest with you. I'm not sure if they have certain kind of ballast that they put in the inhabited area of the aircraft or not. Next time I talk to the PI, I'm going to remember some of these questions. But there's the inner of the two spheres, which is only slightly smaller than the outer sphere, which is attached to that bulkhead, fixed. And so you have that hydraulic high pressure fluid that is able to allow that whole system to float inside there. And the gyros, as you're probably aware, you get big gyros, and gyros, one of their characteristics is when they're spinning hard with a lot of angular momentum, you can push along, rotate around one axis and get a response torque along another. And so we've learned a lot and used that a lot in space to actually point very large spacecraft just with gyroscopes. And so gyroscopes, if they're big enough, they're called control moment gyros sometimes, are able to be, just by commanding a change, and this was actually the case, you may or may not remember, I think I talked to you folks about Saturn, help me out here, not Galileo.
Cassini?
There we go, Cassini. Shame on me. Cassini's pointing for the incredible number of repointing activities going on for that mast full of instruments where none of them were articulated. They all had to be pointed by moving the whole spacecraft and pointing it. That used gyroscopes. And these gyroscopes, you just change speed on them and it changes the angular momentum on that axis and gives you a well-planned, well-controlled torque in a planned area, and you have 3 axes of them, and you can point anywhere with those things. And so I think they use the gyroscopes for a lot of that pointing. Well, I know they do. And yet the gross pointing in terms of elevation and azimuth is done by the way the plane flies. I didn't show you the flight paths. I had another chart on that, but they fly literally 3 or 4 hour legs that aren't straight. They curve because, as you can imagine, you've planned out your viewing, what area of the sky you're looking at, and you plan where you're flying. And so you work out and put it on autopilot, and the computer controls the azimuth of the aircraft, controls the azimuth of the telescope. And you can roll the aircraft if you want to change elevation too. I don't know that they do that, but that would be another way. But the vibration is completely damped out. The buffeting is damped out by that floating bearing. It's just phenomenal.
I mean, how much is it? Like an inch?
I think
a millimeter.
I think it was. I don't hold me to this. I think he may have said a centimeter.
Wow.
Well, yeah. I mean, you don't need much, and of course, high pressure hydraulic fluid in itself. I mean, if it was an inch and you had a disaster, it could be a really bad one.
I would just be afraid if the plane's flying and it's come across turbulence, and then it would just jar and break the mirror, or severe turbulence. Especially if it's only a centimeter,
39,000 feet is fairly friendly.
Well, yeah, for sure. But to get there, or wherever you go, and there, not necessarily when you're using a telescope, but if it's always free floating, you might have a hard landing. But kudos to the pilots, I guess.
I was gonna say I'd love to get a couple of the crew members, for a meeting.
You know what?
Go through this. I bet the stories are great.
Hey, John, my name is Lou Von Verezes. If you ever go up there, let me know, please.
Okay.
I would love to sit in the back there.
Yeah, I mean, if I get to go up, you guys will get offered to talk about it, I'm sure.
Great talk. Thank you very much.
Thank you.
Hey, John, my name's Mark. I have a question. The size of the Webb telescope is, impressive, but if we had the money and the wherewithal to make something like an order of magnitude bigger or even much larger than that, how much more could you see? Is there just a limit at some point to there's not more to see because you've gone back to the beginning of time and there's no stars and it's just all dark? Or could you see higher resolution? So how much, if we really bumped it up, what more could we see?
Well, I mean, there's no question that collecting more photons with a larger area gives you some benefit in looking back. As you now understand better, and I understand better, having just studied this a lot recently, being able to look further into the mid and hopefully eventually into the far infrared will also help in looking back because of the redshift and the fact that there aren't any photons from the earliest galaxies that haven't been shifted well out beyond where that record holder we have at the moment is. But I don't mean to dodge your question, but I'm kind of dodging the question. I don't actually know. I could kind of talk about it, but that's not really what you're asking. I don't know.
Jeremy might know better than myself. I thought that the limit would be around 400,000 light years after the Big Bang because of the light turn on time.
Oh, okay. Yeah. I mean, that is, yeah, in terms of what there is there to see in terms of photons coming through a universe that's transparent, you're exactly right. That is the end of reionization. And and it's also the time, what is it, 360 million years of the cosmic microwave background, because essentially what happened, we're seeing back to the earliest light when we look in the microwave and see that, and now maybe it clicks in like it did for me that, oh yeah, the microwave, that's where very distant light could have started at even in the infrared or in the visible and would be shifted all the way back, all the way over to the millimeter wave, the microwave part of the spectrum. And so that's what we're seeing there. We have to look in the microwave in order to see that because it is redshifted so much.
I have a question from YouTube, from Jeff Newton. It says, does the SOFIA instrument only point out the left side of the aircraft? And does that mean that only half the flight time is available for pointing the instrument in one general direction?
Makes sense to me. I hadn't actually thought of that, but I've got a slide that shows a couple of flight paths, and yes, indeed, they do go out, generally speaking, and come back. And so, and yes, it does only point out the left side there. There's only one big open door. Anyway, you could set up all kinds of scenarios to look at different things, but the two examples that we were given by the PI showed one very long curved leg for the longest part of the viewing, which probably was 3 hours of the flight at least. And no, you can't go back over that again without having to land somewhere where you're not allowed to.
I guess you could look at different parts of the sky, right? If you
yeah. I mean, there's some very busy flights. Just to say that you can't look any longer than the length of one leg. you could take a literally outbound flight and come back, and if the the fuel limit was 8 hours, I don't know that it is, that's probably an average, it'll be half of whatever the time is that the wind conditions and the fuel load allow you to do.
Mhm.
I think
John, would you happen to, I'm sorry. Go ahead,
I've
Henry.
seen a write-up of this, and yes, the short answer is you just find something different to look at on the return leg that's on the other side of the aircraft.
Yep. Yeah, or you go to New Zealand and you see a different part of the heavens.
That'd be nice.
So,
You can
and
sign
when
me
you
up for
have
that
100
one.
when you have 120 missions a year, I'd say a lot of people get their choices of things that they'd like to stare at for half an hour or 2 hours or something like that.
John, would you happen to know where the primary mirror came from? Was it a part of another planned instrument, or did they specifically make it, and where was it made, and so on and so on?
That's a good question. Am I remembering that Hubble is a 2.5 meter? Or maybe I'm
Yes.
thinking, is that right?
Yes, the Hubble's a 2.5, right?
So maybe they just maybe they got number 3 or 4 in the. I don't know. The answer
Okay.
is I don't know. And,
That's fine, John. I was just
I
asking.
imagine if you go out, so there are a bunch of websites. Sophia's got their own. They probably will answer these questions out there.
All right, great. One other question, if you don't mind. On the list of at the very end, one of the last slides, you showed the immediate things they might want to do with it, and they talked again about looking out. I do understand that part, because for me anyway, we had a very good talk not too long ago about satellite galaxies, the Milky Way galaxy, for example, really small, irregular type galaxies and things like that. The better chance of seeing those. But what personally I'm very interested is looking again more toward the center of our own Milky Way galaxy, which we can't do it except in the infrared. So I kind of want to hopefully see that we're going to be pointing that way too, rather than just out.
I wouldn't be surprised. I wouldn't be surprised. I mean, the fact that they're, I could have made that multiple pages long and listed all 130 or whatever there are. If you go out to those web pages, and I'd be happy to show them to you again if you want to, but probably if you just put in STSCI for the Space Telescope Institute and ERS for early release science, or GTO for guaranteed time observation, you'll find those pages.
Wonderful, thank you.
It really is amazing. I mean, I don't know how many of you got a laugh out of the dog. I just love that slide. But when you think about how long these, highly educated, really prepared people have been waiting for their opportunity to get some data here, it's really quite astounding. And yet, when you look how the world has been changed by Hubble in its 25 years or more. What we're going to learn additionally from Webb, I hope, is just going to change things again. I mean, physics has changed completely at both ends, large and small.
Yeah, I'm with you, John. I really hope it does work and work very well, especially considering they're putting it way the hell out there that we can't service it. So,
well, one of my first questions for the project scientists on the Webb a few years ago was asking about servicing missions. And at that time, it was a flat no. There is absolutely no plans, nothing being thought about in terms of that. It's just too far away. Obviously, we could fly out there. I mean, we're going to have the capability, hopefully before long, to do that, demonstrate that capability with Artemis. But it would be, quite an extraordinary thing to do it. And in a way, you have to have almost modularized and planned the initial build to be ready to do anything once you get out there. Having said that, a few years later, the same scientists gave us a talk. We had 2 talks on Webb in the last year. And in one of them, they noted that they put some features on board, not that there was any servicing capability, but in the event that it was developed in the future. So I hope it isn't ever needed. Having said that, in many ways we'd be able to do it, and I would just be really sad if in some way one of the segments actuators break. You know, who knows what it might be. There
Right.
are so many things that might go wrong.
Right.
That first, you know, from October or whenever it gets launched, for 3 or 4 months, we're all going to be holding our breath to see.
I agree.
Hey, John, can I ask you another question? I was curious when you were discussing the Lagrange points. You're saying that this is going to be on L2, right? Was that correct? It's right
Yes.
behind me. So I'm curious, how much energy is required to keep that orbit? I mean, do you have what's going on with that? How
Well,
are you monitoring and maintaining that?
Yeah, the answer is some. I'm sorry I don't have a better answer, but the fact is that even if you're at one of the stable points, the universe is all about perturbations.
Well, sure.
I mean, astrodynamics was my field, and so I used to do these orbital calculations. I mean, they don't in fact go straight out to L2 and then turn left and go a little bit away and then circularize where they are. And they don't do it for two reasons. One is that would be really a stupid way to use energy. But the other one is this massive telescope with the solar radiation pressure on it at various angles has to be guided into its final orbit in a very kind of a gentle way. So as they go most of the way out straight, toward the end, they will actually kind of swoop up and around until they finally form just the right, you can almost picture it like a Lissajous pattern if you have an oscilloscope and you're familiar with those, but it's a certain geometry that they smooth out in order to not stress any of the mechanical aspects of the now fully open and configured spacecraft. And yet to end up with, if you will, the bottom end of it with the sun shield always pointed back towards the sun.
Yeah, John,
but to answer your question about how much energy, yes, it will take energy. Even if you go to an L2 point and want to stay right there, it takes station keeping, and that's a certain amount of energy from time to time. So they have to have some capability on board. Now they've got some ways to use, I believe, radiation thrust, but I could be wrong about that. You know, the reflection, if you will, of solar radiation or the absorption of it. They've got panels for that to trim things, but I'm not sure what actually the propulsion system is that they have on board for it. I need to look into that.
Probably hydrazine.
Yeah, that's often what it is.
Wow, I mean, now you just opened me up to like 8,000 other questions, so I'm going to just stop right now.
John, do you know when they open up the telescope? Do they open it up close to Earth, or do they wait till they get to L2?
Yes, and it's close to Earth. Now,
oh, great.
I encourage you all, we all have, people suggest way too many YouTube videos to look at than anybody could in a lifetime. But if you just put in if you just put in YouTube JWST, you'll be led to one of the top ones are these really well produced. They're usually, there are a couple of them that are as short as 3 minutes or so, but some of them are 10 minutes or so long. And they take you from launch right through all the stages as you go out, you know, the first 8 hours, the first day, the first 3 days, what happens then at 10 days, you know, this flap comes out, that opens up the wings, if you will, which is the last 6 panels, 6 segments of the 18 segment mirror come out, I'm going to say somewhere before halfway out there. So before 2 weeks, maybe in the first week they go out. And then the secondary is erected, you know, in place. And at that point, you have the full primary secondary configuration. And then they open the sun shield, the solar shields underneath. And that's quite an affair. And that's all shown beautifully in these videos that you can go out and look at on YouTube. Anything else?
Speaking of energy, if the telescope needed a significant repair, could you send out a small robot tug and just bring it back to low Earth orbit, where it would be easier for a human crew to get at it and do the actual work?
I'm sorry, the low Earth orbit would be for what?
If it needed a significant repair, could you use a robot tug to bring it back to low Earth orbit where it's more accessible?
I mean, you certainly could.
Henry, I'll help you design it.
I'm not sure if they put toe points on it, but little lugs here and there. But seriously, I mean, that's certainly possible.
There are a series of satellites that have been designed that way, with multiple launches of service of the satellites that are supposed to work with service vehicles, and some of these service vehicles are supposed to be out of service up to, I think, 3 or 4 different satellites. So I know they've designed systems like that. It wouldn't surprise me if they decide they need something like that for far-flung telescopes.
Yeah, it's a popular thought now to stage things. And so staging cryogenic fuels in various parts of the Earth-Moon system permanently, so you can go visit them to tank up once in a while, is one of the things they're talking about too.
They can keep beer cool there too.
Real cool.
A new approach to geocaching, I suppose. Any other questions for John?
John, what would be the limiting factor on the life of the Webb telescope? The cryogenic cooling?
Good question. I don't know. Nobody asked the folks when I was talking to them. Let's see. I would guess so. I think that's an active component, and so that would kick out one instrument if you couldn't get down to those temperatures. I don't know how the rest of you felt about that micro shutter array, but I just think that's brilliant. Being able to get individual spectra. Okay.
Well, thanks very much, John. We hope to see you again.
I enjoyed it. And,
under safer times.
I will, even if you guys meet physically again, I may come in harm's way and see you there.
Love to see you.
That'd be great, John.
Yeah, will we ever be back?
Thank you.
I appreciate your attention, and I enjoyed it. Thank you.
Thank you very much.
Thank you.
Thanks, John.
All right.
With that in mind, and if anybody has anything for the good of the order, we will end the YouTube recording.
You know what? I did want to mention something to the club for anyone who's interested in participating. This month's astrophotography challenge, if you're so inclined, is the Rosette Nebula. If you decide to take it, you could post it on the astrophotography forum, and if you do, make sure you sign up and subscribe to it. But everybody who is subscribed to it will see it. So if anyone who takes any pictures, please, yes, share it on the group's IO, but put it on the website. Show it off on the astrophotography forum. And that way, people that are learning can ask questions if they see someone has done something they want to do, etc. Okay.
And let me reiterate that, because Lou is sort of Lou and Irv and a number of our members, Richard Steinberg, are spectacular astrophotographers, and the stuff they put out is spectacular. But every once in a while, poor schlub like me puts my phone on a tripod or something and takes a shot, and I get a decent shot once in a while, and put it on the listserv. Put it out there. Sometimes somebody else's photo is somebody else really likes to see it. So don't be shy just because you're not a pro. This is the Delaware Valley amateur astronomers. We're all amateurs.
I had just seen a YouTube video on how to do astrophotography with an iPhone 12.
Is that amazing?
Mm-hmm.
Who would have thought?
Mm-hmm.
I wouldn't have 20 years ago that you would even be using a digital camera. Forget astrophotography. 10 years ago, an iPhone would never get a picture of a star. And now, why do you have a DSLR? Just use your damn phone.
Yeah. Yeah. Well, Jeremy, let's terminate the YouTube video and move to